Okay, so last time, so what we've been doing so far in class is, a lot of inductive proofs. Oh, look, here's something that's true. Let's show it by induction. I'm going to do the opposite here. I am going to inductively figure out what this is, and then I'm going to leave it for you to prove. I'm not going to go through the proof because the proof is almost identically to the construction that we do to figure this out. And I think it's a good exercise if you try to do this on your own once we figure out what the formula is. Okay, so we want to figure out what this integral is from 0 to the power of 2. And as I mentioned, this is very important if you want to compute the volume of an n-dimensional sphere. So I'm going to do this. The first thing I'm going to do is I'm going to call this something. I'm going to call this I2n, signifying power here. And so what I'm doing is I'm sort of setting up here to kind of do something, break it up and do it my parts. We got about this far, it's what he pointed out to me last time, because 1 minus sine squared x. And so I can massage it a little bit further. And of course, this, I'm going to break this up into 2 pieces here. Let me point out this is the same integral we started with, just with 2 less powers on the cosine. Right? So what I have now, really, so I have I2n is I2n minus 2 minus this mess right here, which because of my dramatic flair, I've written out as cosine 2n minus 1. I'm sorry, cosine 2n minus 2 sine 8 sine x. Anybody know how we might try to integrate this? Anybody have even part of an idea? Like parts? Good call. This thing right here, I'm going to do this. Now, this is a more complicated piece that I'm usually used to doing parts, but I'm going to do this. Cosine 2n minus 2 x sine x dx. Now, if I remember right in parts, I've got to be able to just kind of integrate this in my head here. Taking the derivative of sine is easier, but does anybody see the trick here? Notice sine x is essentially the derivative of cosine up to a sine. And so this allows me to write this. Let me check and make sure that I've got this. The derivative of cosine to that power, bring it down, it's going to be minus cosine 2n minus 2. That's the derivative of cosine, it's minus sine. So I sort of took this apart so that this thing could be integrated. So I get I2n equals I2n minus 2 minus let's see, the product of these is going to be actually back to plus. Cosine 2n minus 2, cosine 2n minus 1 x sine x. And then it's going to be plus minus 1 over 2n minus 1 cosine 2n x. So I'll put this together where this piece came from, and then I subtracted off this. And remember, the whole thing is subtracted off in the first place. Okay. Now, a couple of nice little miracles happen. First of all, this one goes away. That's gone. Because when I plug in pi over 2, I get 0 for cosine. If I plug in 0, I get 0 for sine. So poof, that's gone. And what is this right here? This is, that's right, this is just I2n, right? So actually, I've reduced this all to algebra in the following sense. This equation becomes I2n is equal to I2n minus 2 minus 1 over 2n minus 1 I2n. Everybody agree with that? And this allows me to solve this equation here. So this is going to be 2n minus 1 plus 1. So this is going to be 2n over 2n minus 1 I2n. This gives me a formula of how to get the next interval from the previous one. So let's see if we can see a pattern. Mathematics is often about finding patterns. And so we'll see what we can do here. Any questions so far? I need a seed to start this because this is kind of inductive. Right? I0 is pi over 2, right? Because what happens when n is 0? This is integrating 1, right? From 0 to pi over 2, which is going to be pi over 2. Everybody okay with it? And once I've got my seed, I can let it grow using this formula here, right? So when I want I2, by this formula here, that's 1 less than 2. So I get pi over 2 times half. I4 is 3/4 of I2, right? So it's just 3/4 tacked onto this. I6 is 5/6 of I4, so it's 5/6 of this. I8 should be 7/8 of the previous. So let's see if we can make it. And then I'm gonna doll it up. I2n. Well, again, it's about finding patterns. What pattern? The first thing I see in my patterns, every time I get a pi over 2, right? and then I've got this awful fraction. Huh? What's the pattern of what happens after pi over 2 in the bottom of the fraction? Think about only the bottom. What happens at the bottom? Oh, right. It looks like it's even numbers, right? 2, 4, 6. And the question is where do we end? Notice where we end matches the subscript, right? It's a good thing. Now I'm going to go back to what you said, Nick, because you were talking about top and bottom. What happens at the top? Everything's one less. So, well, yeah, that's right. That's the patterns of these others. Right? Now there's a more concise way to write this if you want. Okay, the first thing I'm going to do is neither one of these is a factorial. Why is the top not a factorial?
The numbers are omitted.
The even numbers are omitted. So let me massage this. Okay. So I'm going to shorten my notation. I'm going to put the evens in. Right? Nothing wrong with that. Well, so far there's something wrong with it. How do I fix it? We'll put the same crap at the bottom, right? And actually, that's a good observation. That's essentially what I'm doing, isn't it? So what am I left with on top? Well, this is pi over 2. What can somebody tell me a concise way to write the top? It's 2n factorial. Everybody agree? Now let me take a little sidebar here. Notice that this is not a factorial, but if I pull a 2 out of everything, it is, right? If I pull a 2 out of this, it's 1. If I pull a 2 out of this, it's a 2. If I pull a 2 out of this, it's a 3, and so forth. This is actually 2 to the n times n factorial. Right? Because if I pull n factors of 2 out, then I've got a 2 to the n, and then I've got 1 times 2 times 3 all the way up to the n. So what do I have in the bottom? I have 2 to the n times n factorial, 2 to the n times n factorial. So my formula turns out to be pi over 2. Factorial, and then I square the bottom as was observed earlier. There's the formula for that. See how we did that kind of inductively, right? We built on the previous case to get that. Now, here's my exercise for you all. Now, go home and try to prove that. And try to do it. Try to do it for the signs to get the odd case, as a matter of fact. Okay, let me go over a couple of things here. Just kind of finish off this business with induction. I'm not gonna prove the first two, but I'm gonna prove the last one. So principle. So we've used some of this stuff sort of at least implicitly. I'm gonna make it formal. This is called generalized principle of mathematical induction. Principle of mathematical induction. And it looks very much like induction in the following sense. Let K well, let S be a subset with following properties. Number one, K is an S. For some K in the integers. Here, I'm going to say two, if N is an S, then N plus one. What do you suppose this is going to say? What property I guess has here? The principle of mathematical induction was when K equals one, right? We said one is an S, and if N is an S, and N plus one is an S. Now, our starting point is K, right? Then S contains all natural numbers. Numbers greater than or equal to K. So here is just, basically what this says is you can start, your bottom rung of the ladder doesn't necessarily have to be at one, you can make it be at some K, and then you have K plus one, K plus two, if that's what's appropriate for your problem. And let me give you this one. I proved this one in the notes. I'm gonna skip it over. After this, I'm gonna show you one last thing that I claimed earlier. This is called complete induction. So here I'm formally writing down what we talked about earlier. We've actually used the principle of complete induction, which I will sometimes call PCI short. We actually used that in the postage stamp problem that we did last time. Remember the one where we said, okay, any amount of postage 6 cents or more can be taken care of with only using 3 and 4 cent stamps. So I'm going to state this one formally here. Suppose S is a subset of N. Where the problem that if that for all natural numbers, you know, 1, 2, 3, up to N minus 1 is a subset of S, then N is an S. Then S is all of them. So now what we're doing is we're assuming not just if N is an S and the next one is S, we're assuming that if you have all the ladders, if you have everything on the ladder implies that you've got the next step, then it's all of them. This is probably not surprising. We show the equivalence of this in the notes. You can look over it, but this is the one where instead of only using one run, we're able to use all the previous runs up from and including the base cases. Okay. And this last one, I'm going to actually prove. I'm going to couch this theorem. And you've heard me say this before. The principle of mathematical induction is equivalent to the statement that all nonempty subsets of the natural numbers have a small statement. Sometimes it's called well ordering principle, and we're going to talk more about well ordering in other contexts as well. So we've used this one actually early on, haven't we? You remember when I kind of teased you like this early on, and I said, what is true of the non-empty subset of natural numbers? You all were able to kind of guess, well, it's got a smallest element. This is actually equivalent to the statement of induction. So let's see why this is true. So we've actually been induction we've sort of known for a while, only it's in disguise a little bit. Suppose principle of mathematical induction holds. And we want to show that it must be the case that every non-empty subset of the natural numbers has a smallest element. We show P has a smallest element. So we're assuming that the principle of mathematical induction holds. We pull out some random non-empty subset of the natural numbers, and somehow we've got to convince ourselves that this non-empty subset has a smallest element. If P is equal to the natural numbers, then this is true as one single statement. So if T is all the natural numbers, then T contains one, and one is the smallest natural number. So if T contains it, it's going to be the smallest element of T. Everybody agree with that? So let's suppose not. Then if you take the natural numbers and you take away n, or I'm sorry, if you take the natural numbers, take away t, if I call this s, this is not n. So if t is a proper subset of n, then when I pull all t out, there's got to be some stuff left over, right? We assume that t has no minimal element. And let's try to get contradiction. Well, note that one is in S because if one is in T, then T has a minimal element. Okay, so notice you might guess that I'm building up sort of for induction. Now assume Now, since we have some n and s, now let me, make the following argument. Note that 1, 2, 3, all the way up to n must also be. As if any were missing, the smallest missing element would be minimal element C. One must be an S, because if it's not an S, it's in T, and it'd be the smallest element. Now let's suppose that n is an S. Well, all the numbers up to n have to be an S, because if any of these are missing, just take the smallest one, that's in T, and that would be the minimal element, of T, which we have assumed does not exist. So then, n plus one is an S. If not, it would be smallest element. So here's what we know. S has properties. One is in S. And two, if n is in S, then n plus one is in S. Right? We've shown that one is an S, and if n is an S, then n plus one is an S. And we also know that the principle of mathematical induction holds. So what does this mean about my mystery set S? Good. S is equal to n. So T is equal to the empty set, and this is not. And so this establishes the first relation. So what we have so far is a principle of mathematical induction holds, then every non-empty subset of the natural numbers must have the smallest element. Let's go the other direction. Now suppose every display every non-empty subset of the natural numbers has a smallest element. And now we need to show principle of mathematical induction holds. So to show that induction holds, let's do the following. Let S be a subset such that one So suppose we have a subset of the natural numbers that satisfies those two criteria. That is, one's in S, and if you have any natural number in S, then the next one's in S. We want to show, well, what we want to show is that S is all the natural numbers. So let's let let's suppose that, T is in with the set S removed. If T is not empty, then what must be true? What are we assuming? If you have a non-empty subset of the natural numbers, which this is, then it has a smallest element. So if T is not empty, then there exists smallest element. By the way, let me point out that K cannot be one. Anybody tell me why?
One is S.
Right, we've assumed at the outset that one's an S, so it can't be in the complement of S. Right? I agree with that. So one for sure is not in there. So, one, two, all the way up to K minus one is an S. But by assumption on S, K is an S, which is a contradiction. Therefore, T must be the empty set, right? Because if it's not empty, it's got a smallest element that by induction can't be there. So this implies that S is all in. Because if T is empty, that must mean S is all in. So we have PMI. Okay. Any questions? Questions? Okay, so this is, we're going to start and get mostly through, I hope today, the last section that will be covered, this counting section on the first exams. Counting is actually one of the most important things you do in math. It's a lot more sophisticated than just, counting your Easter eggs or something like that, or at least it can be. We're going to introduce some of the tools of counting, how many objects are in a set, and actually later in the course, we're going to count the infinite, so to speak. So let me recall this notation. If S is a set, this collection of things, then is cardinality, sometimes called order of the set. If S is equal to A1, A2, AM, then sometimes we say the order of S. So for right now, we've only got two kinds of sets. Ones that are finite. So there's only finitely many. Some usual counting number describes how many objects are in that set. And the other kind of set is infinite. And we don't make any distinctions at this point, right? So for example, the infinite sets, the natural numbers, the real numbers, the rational numbers, things of this nature, right? Here is the first counting theorem. Let me call it more things probably. Theorem down. S T sets are disjoint Anybody recall when we're means for two sets to be disjoint? More than that.
Not substance, subset.
Still a little bit more, right?
Their intersection is then all set.
That's right, there's no overlap whatsoever, right? Right, nothing in common. Right? So here's the first counting theorem, and I bet you can figure this out. If I have a bag of apples and there's 20 of them, and I have a bag of oranges and there's 30 of them, how many fruits do I have? 50. How did you do that? That's right. And apples and oranges are different, right? So theorem. 241. Let A be the disjoint sets with the order of A, M, and the order of B, N. Then how many elements are in a union P? And this is something this way. Okay, so here is a more right. So let's do this. This is probably no surprise either. We're at AI. I do a collection, finite collection of pairwise disjoint sets. That is to say, AI intersect AJ is empty. If I include it. That's what I mean by pair, in no pairs or any overlap. Anybody want to guess this? It's a number of things in the first, number of things in the second, number of things third, all the way up to stack them up. That's it. If they're disjoint. Um. Uh, 2.2, using our basic fact. How do you suppose we want to do this?
A meter pairwise or. Yeah, A meter pairwise disjoint sets.
So this way. That's essentially what we do, which is written out longhand. How about induction? Ooh, I can do n equals 1. Right? That was a little bit silly. This is the interesting base case, because this is really previous theorem. That's the content of this theorem, right? But now, let's do our inductive hypothesis here. Now, inductive hypothesis. Now suppose for some m greater than 2, we have A1 union A2 union AM equals A1 plus A2 plus AM. And we want to look at the next case, right? Any questions on how we might proceed? That might help. I claim that A m plus 1 and A1 union A2 union AM are disjoint. Huh. Anybody explain why this must be true? Okay, well, all the pieces are disjoint. Let me be more formal. Suppose X is in A m plus 1 intersect A1 union A1. So X is in AM plus 1, and X is in A1 union. So I'm gonna write that up for dramatic purposes here. What does it mean for X to live in this union? It has to live, if you're gonna live in the United States, folks, you gotta live in one of the states, right? And so X lives in the United A's, right? So it has to live in one of them. So I between them and them. Does anybody see a problem with this? What do we know? We know X lives in the state AI. And X also lives in A plus one. Exactly. X is in A plus one intersect AI, which is the empty, which is equal to the empty set. Because we claimed that all the little babies were disjoint, right? And this is a contradiction. So, AM and A1 UN are also disjoint. Pray tell, how does that help? Let's call this set B, right? This and this are disjoint sets. So by inductive hypothesis, or by base case, we have that this has got to equal I agree. But by the inductive hypothesis, and this is by the inductive hypothesis, and so we're done. Right. So basically 2.4.1, our statement supplied us with a base case, and then we were able to induct and build this. Okay, any questions? Any questions? Okay, so I'm going to give you all perhaps one more theorem here. This is kind of the first step. This theorem. So really what it says is accounting is easy if you have disjoint sets, right? You know, for example, if I want to count the people in this room, I can just count people over here. That's one set. Call you all the right set, and you're over here. Call you all the left set. I can count this. They're disjoint. There's nobody sitting on both the right and the left. So add them up and I get everybody in the room. That's essentially what this says. What happens if there's overlap? Right. That's essentially it. So theorem. If A given finite sets, then write two of these down. One. How many elements are in A union B? It's exactly as Nick said. Just add everything up. But oops, I might have counted too much. So take away the people that I counted double. Notice mathematics always takes care of you because what happens if the sets A and B are disjoint?
Intersection.
Then this is empty and you get a big fat zero. So this collapses to the previous formula in the case it's disjoint. Always check your formulas for stuff like that. Like I said, the math will take care of you. And this is just really reworking this. I will leave you with the following question. what happens if I take the kid gloves off and I don't make any argument about it? I don't make any claims about this joint or anything else. What happens here? So think about that, and we will get back to the counting next time. Does anybody have any questions? All right, y'all have a good one, and we will see you on Tuesday. Any questions out there? See you next time.